start the recording, I believe.
Friends, very sorry about this or disruptions and whatever. So we got delayed, but let us get started. So this is what we had started discussing. We are discussing the handling of declarations, specifically when we have types which are not just simple types. So on left, we see the grammar that we had used for declaring simple variables. And this is a form of the grammar which is inherited attribute because the non-terminal B here produces int or float and then T produces B. So you can see in rule 1, in T we get the type and then later on we get the list of variables. So when we reduce by rule 4 or rule 3, at that time the type is not directly available as a synthesized attribute. We have to get it from T, and we have seen different techniques for doing that. We will revisit those again. Now, on the right, I'm trying to introduce just arrays. So if I have an array, then you see I have made changes to the rules 3 and 4 and introduced 2 new rules, 8 and 9. So in rule 3 and 4, after the identifier, I have introduced a new non-terminal, which is C. This non-terminal is what is to expand into the different dimensions of the array if the identifier is an array. Otherwise, by rule 9, it could be epsilon, wherein the same grammar will also handle simple identifiers. Now, in terms of the rule 8, which is the recursive rule for C, which will, within square bracket, put constants in a recursive form, are the different dimensions of the array that might be declared, and it will end with C being epsilon by rule 9. And we highlighted that this particular recursion in rule 8 is a right recursion. The reason for that being that when we want to process the declaration, we need to first know the innermost dimension. So when we have an array int A 2, 3, the example that we had used earlier, if I may go back to that, or say let's so if we go back to this example, then int 2, 3. So 3 is the innermost dimension. So this is defining an array of 3 elements, each being an integer. And then it becomes itself a type of a row array having 3 elements. And then you come to the next dimension, which is an array of such row arrays. So 2 such elements will be there. So in this way, we can see that if we want to, when we need to process the declaration, we need to have the information from the right end of the series of dimensions that we give in an array and move towards the left. And for doing that, I need a tree which is right oriented, and therefore I use a right recursion. If we use the left recursion, then we will have several issues of carrying forward the types of the inner dimensions. On the other hand, when we are actually accessing an element of the array, which is by, you see at the bottom of this slide, A produces A, then I still have left recursion because at that time, we already know what the dimensions are. So we know the type of the sub array in every place. and we just have to compute the offset, which certainly has to go from the outermost dimension, the first offset, in terms of arrays, in terms of how many rows you have of the 3-column array, and then to the specific offset within the particular row. So it has to go from left to right. Information has to flow from left to right. So you have a left recursion. So this is a basic insight of why this is a right recursion. And the hello. Okay, I'll share again. I don't know what is going on.
Yeah, no, it's fine.
Is it? It is okay now.
Yes.
It's also at times. Anyway, so this is I'm highlighting on this right recursive form of the rule here, because as we'll see that if we want to handle the same grammar using kind of a transforming it to using synthesized attribute, this right recursive rule will actually cause a lot of pain, and we'll see why that is a difficulty, but we'll come to that story later on. For now, so using those kind of declarations, this is, I'm going to the next slide on this gives a couple of example declarations, and this is what we are trying to do in this case. Handling of types. Given these declarations, we want to create the instance of the symbol table, making entries for these declarations, and for each one, we want to specify what the type is, and that is what is explained in this example. And this is the array builder that we have used here. Now, I will take a little bit of deviation to talk about type expressions in general, because as you can see that, there are types which are built in, which are predefined simple types, like integer, like float, double, bool, etc. But there are a lot of types that are built up using type constructors, and we'll see what do they mean. So type expressions are kind of, these are expressions of type, and that is what is somewhat of a different concept than expressions of value. So we have always talked about expressions of value, like 2 plus 3 or x plus 5 or a5 into 7, these are expressions of value. But here we are talking about expressions of type, that is how can types be composed to build other types, and they can again be used to build a bigger type and so on. Now, these are important in the applications in particularly two ways. One is we need to check for types. So we say all these kind of requirements are put under the title of type checking. So these are logical rules to reason about the behavior of a program at runtime. So if the more type specific, the more type consistent a program is, it certainly gets easier to analyze, translate, as well as make sure that it will run correctly at the runtime. So we have seen some examples of this earlier when we talked about type conversion between integer and double, or between integer and full, and so on. So being able to check for types is a basic requirement for which we need this type expression. So the types of the operands have to match the type expected by an operator. It's the basic requirement of type checking. So anywhere, this compatibility is very important between type expression. We will take examples, do not get worried if we are not following it 100%. The other class of applications of type expressions are applications in translation. So when we are doing this translation, there are different information that we need to actually compute. For example, we need to determine the storage that will be needed for that name at runtime. Right? So we need to determine the size of the storage. We need to determine the organization of the store. Like in case of arrays, we have seen that if there are multidimensional arrays, then there is a row major order of specifying, laying up that out in terms of a linear memory. So all these are dependent on the time. So determination of storage is an important translation application. We need to calculate the address denoted by array reference. We have already seen that. We need to insert explicit type conversions. I mean, there are, you know that you can cast one type into another, which means that I can take one type expression and convert it to another type expression under certain conditions. And that could happen by explicit specification by the programmer. Also, we need to choose the right version of arithmetic operation, and so on. I mean, this list is not exhaustive. So if we are adding two integer types, then we have to have an integer operator. And if we are adding two double types, then we will have a double operator. And you know that, for example, in C++, you have overloading of operators. So you can define your own operators, the existing operator symbols, you can redefine their semantics, and you have to make sure that they are applied to the right kind of type operators, right kind of operands, and if there are multiple such overloaded operators, then the right version of the operator has to be. So these are the different requirements or applications of type expression. Now, to simply specify what is a type expression, a type expression is either a basic type, which is given, or it is formed by applying type constructor operator to a type expression. Type constructor is an important factor. The sets of basic types and constructors are dependent on the language. So the language specifies what kind of basic types are there. For example, most of the languages have some form of array type constructor. So this is the example that we are seeing in C. So if this is the expression for the type construction, then this graph or this tree could be the type expression. So what it is saying that I have a type constructor array which takes two elements, two operands. One is an integer, which is the dimension of the array, and the other is the type of every element. And from that, it builds an array. So that is the constructor, which is by itself a type expression. So array 3 integer, which is the right part of the subtree, is by itself a type expression, and it is a type noun. And therefore, it can in turn be used in the further type array constructor here on top, where you have a dimension 2 and an element type, which is an array of 3. And you get a bigger type expression. So these kind of array 3 integer or array 2 of array 3 integer, these are examples of type expressions. Now, type expressions, as I said, that could be basic types like bool, char, int. These are some of the float, double. These are some of the basic types available. See, there are obviously a number of qualifiers also available, like short, long, and all those. There is a special type expression or basic type called void, which denotes the absence of any value. So, it denotes just the placeholder. That this is a specific expression where a type is expected, but no type is actually there. So I call a function without parameter. So I can specify that it is called with the type void. So this is kind of, every algebra you define. So since it is a type expression, so you're actually defining an algebra of types. So on that, every algebra you define, there is going to be a zero of the system. Every algebra, whether it's integer algebra, whether it's floating point, everything has a zero. So void is the zero of the type. Now, I can have a type name. A type name is a type expression. So type name is like I have an expression as we have shown. The whole thing, array 3 integer, can be called a type name. I can have different operations on the types, like I can have a Cartesian product. For example, S and T being two types, S cross T represent a list of tuple of types. So, for example, if I have a function taking the first parameter int and the second parameter double, then the type of parameter of the function is int cross double, which says that it takes a pair. So this is also becoming another constructor. So this is another type constructor which takes builds pairs of types, where the first of the pair is an integer and the second of the pair is a double. And finally, like in any algebra, like in any expression, I can have variables. So I can have type variables as well, which are names, specific variable names given to types. And it is also possible that compiler will generate type variable. Right. So this is kind of a whole thing of computation based on deducing the types of different expressions and variables which happen at the compilation time. And in terms of languages like C++ or Java, which are kind of strongly typed, there is a whole lot of features on that. We may not, for example, if you must be aware of templates in C++. Those are basically generalizations of how you can write types in general, typeless expressions. We will not go to that depth, but let us see a little bit more of the type expressions. So some of the type constructors we have already seen. Array type constructor in 10.5 we'll be using the type constructor array, as we have seen. Another very common builder that we have in C++ are records or structures. We say struct, where there are multiple components, each having different types, and this is just a collection of those components. And there is no, unlike array, there is no specific ordering of these components. Rather, they are referenced by their name. So such a builder is typically written in this way. So I can say the type constructor type record for struct is a record. So this is the builder. Like array is a type constructor. Similarly, record is a type constructor. And this is a set. As you can see, I am using curly brace because the ordering of the components are important for the layout, but not important for the semantics. I do not need to know whether name occurs first in the memory or height occurs first in the memory. All that I need is I have a component name, which in turn has a type expression cat20. So if I write using the builder notation, it will become array20 cat. And then we have another component which having name height, which has a type. So these are the type constructors that you can have. So using that, we do the typical. We will be able to do the typical, type checking and equivalences. So this is just an example to illustrate. So I have a structure type here, having the name and weight as these components. And I have given it aliased, given it a name, a person. I have another structure which has exactly the same structure, except that it has different names for the component, but actually the same types. And I give it a name student. And then I define the variable P of type person. the first type, and variable s and t of the second type. Now, these are, forget about the cout values and stuff. These are just for checking. Now, if I want to do an assignment of P to S, or rather, let's take the next one. If I do an assignment of S to T, then we will say this is a compatible type. Why is it a compatible type? Because the type of S is student, for which I have a type expression in terms of record, sname, cat20, height, int. And for T also, I will have the same type expression. And both of them have the name student. So I'll say that this assignment operation, which is defined only between compatible types, is allowed here. Whereas if I want to assign P to S, I will have P as a type of person, which is record, name, cat20, and weight int, and S, which is of student type. You can see in terms of the actual size of the components and their respective types, these are all identical. But even then, this is not, this is considered incompatible because they have different type expressions. So the assignment operator, the normal assignment operator, will not allow this kind of assignment to be done, and type expressions will reject. So that's the kind of use. I just use struct to give some illustrations to you of something different from array as a constructor. So extending on type constructors besides array and structure, the other main two constructors we have, one is a function type, which takes variables, parameters of 0 or more types and computes the result type. So if I have a function f, which takes an integer, gives an integer, then we show it by this mapping. If we have add, then first a type construction is done using the Cartesian product, and then I get the function construction by int crossing goes to int. Similarly, the type of main can be specified. So these are the different constructors. So we have a function type constructor. So we have by now seen 4 different constructors: array constructor, Cartesian product constructor, record constructor or struct constructor, and function constructor. Similarly, if we have a pointer type, like which is an address type. So if I have int start p, then the type expression for that, the type is address. So it is giving an address of int. So address int is the constructed type. So these are the different types of constructors. You can have more, obviously, depending on the language, but these are some of the very common ones. So just to see some examples of compatibility and what kind of different things you can do. So we say 2 type expressions are equal or equivalent, and if they are, then using them returns a certain type because they are equivalent. Otherwise, it will return an error. So that's the incompatibility. So you have type def int star int ptr. So int ptr is a type which has expression address int. Okay. Then you have type def int ptr array 10. So int ptr array 10 is a type expression which is array 10 int ptr, because that is the base type. That is the element type. I'm sorry, this is the element type. Now int ptr in turn is address int. So this is array 10 address int is the type expression for int ptr array. Now I also type def iptr array in a different way, not using the int ptr, directly writing int star here. So this clearly is array of 10 of int star, which is addressing. So you can see that these are the different type expressions that are getting generated. And then I declare different variables. This I declare directly, which is of type variable int ptr array. The next one y is IPTR array. Next, I've just directly defined int star z type. So the type T of that, I mean, whatever, just to give it a name, is array 10 address int. So you can see that all three of them are actually resolving to the same type expression, array 10 address int, and therefore they are equal or equivalent types. Just to take another example in function, let's say I do a type def for a function pointer. So what is FPTR? FPTR is a function pointer.
Sir?
For a function. Yes.
Sir, you have to reshare again.
Okay.
But I am able to see anyway.
Is it visible now?
Yes,
Yes,
sir.
yes.
Sorry about that. So continuing, I have say another example using functions. So FPTR is a function pointer which represents a function which takes two integers and return it. And F is a function itself which takes two integers and return it. So what is FPTR? FPTR is a pointer. So it is in terms of construction, it is an address. Address of what? A function which takes two integers, so int cross int, and gives a result which is int. So int cross int goes to int. Now, if I take function f and take address of that, ampersand f, then I'll get address, and similarly I'll get int cross int, giving int. So you can see that FPTR and ampersand f have the same type. Now, this is something interesting, that if I take the type of f, then I'll get int cross int, giving me int. But in C or C++, this also is taken to be equivalent, because if you talk about a function, then you are necessarily talking about its address, even if you are not explicitly that. So type equivalence not always is only about just matching the expression one to one, and that may not be so easy to do, but there will be more complex rules to do that. Usually type expressions are represented by graphs, and two types are structurally equivalent if either they are of the same basic type, I mean both are in, both are good, something like that. They are formed by applying the same constructor to structurally equivalent types, right? As we are doing here, we are using array constructor in the case of IntPTR array, or we are using IPTR array, and we are applying it to the structurally equivalent types address int, or one is a type name that denotes the other. For example, IntPTR here is a type name which is equivalent to address int, because IntPTR represents address int, right? So in such cases, the types are taken to be equivalent. So this is, I mean, we will not go into the detailed, algorithms of how to do this. I just wanted you to understand that such things happen in terms of checking the types of variables and expressions, so that semantic actions can be made sense. Okay.
Sir, your voice is not audible.
Voice is not audible. ISG, can you hear?
Yeah, it is audible now.
Yeah, now
Fine.
sometimes sometimes the volume is decreasing actually.
Yes,
Okay.
sir.
Okay, so that was about, that was just an overview of type expressions. Let me stop here once and see if there is any question. So otherwise I'll move on to the actual Is there any question, friends? No. So let me.
Syllabus of the test.
That is a different question.
Yes.
Okay, I'm sharing again. I hope it is visible and I'm audible. Okay, so how do we translate in the presence of array declarations? So this is the extended grammar that we have seen already with this rule of introduced. So you can very easily see here that you need inherited attributes because okay, one point I must highlight here is earlier in the earlier grammar we had a list of variables. I've just simplified that by using a single variable in a declaration. So if there are 5 variables, there will have to be 5 declarations. You cannot write int a comma. That is just to simplify the recursion on the variable list, which is not critical for understanding the processing of arrays. Okay, so that was just it. Now, if you look into this rule 1, production rule 1, then T will get its type first because T produces B and B produces whatever, and that's on the left. So this is what T will get the type, and then the reductions in C has to happen. You know, so and it will obviously start with, this is right recursive, so this will obviously start with C producing epsilon, and then you will have rule 8 applied a couple of times. And when you do that, it is to start with itself, it is important to know what is the element type, which is actually available in terms of what you got in. So this is not synthesized. So this is a case of an inherited attribute, and we will use a scheme of using global marker that we had discussed for handling. So let us go over. So there's a typo. This B will have to be removed. I'll correct that. So these are the attributes that I'm planning. I'll have a type.
PPT, can you see, can you just share the screen once more?
What is happening?
Yeah, fine.
Is it okay now?
Yes, fine.
Okay. So I have a type attribute for B and this with not B and sorry, B is T should also be mentioned. I have a type for weight. I have an attribute for weight, which is the weight of the type, and then I have a variable T to pass the type information from the B node to the production C producing epsilon, which is the inherited one. So this is kind of a global variable, and W is the width of that type. So T and W are basically global values, whereas type and width are associated attributes of non-terminals B, C, T, and so on. So with that, we revisit the rules. This is the first rule, which is the whole list of declarations. So we have an epsilon production here. So earlier we wrote it as M, wrote offset set to 0 with M producing epsilon. This is just an alternate way of writing that, where the action before the symbol D, which actually translates to having an epsilon production, M producing epsilon, and offset is set to 0. So this is the point where the whole processing of the declarations is starting, and we keep.
So really sorry, but that's not coming up in the screen. Again, you have to reshare. Can you re-log in then once? It's happening too often now.
I don't know. Sometimes it's coming fine with me because right now I can see the screen, but someone else is not.
I'm not able to see it. So I
And we
don't
can
know.
also see.
Okay, I'll log out and log in once.
Sir, it is visible.
Yes.
It is visible, sir.
Yes. Yeah, but it's intermittent possible. Let me just log out and come. Is it visible now?
Yes, yes, it is. It was, but again, yeah,
Yes.
that's fine.
Okay. So in this offset 0, at the beginning of the series of declarations, we are setting the offset to 0 because that's where the counter for the symbol table starts. Now the key is this production one, where I have to set the type of T, because I know that I have computed the element type earlier based on, if I go, I have computed the starting the element type here in reproducing it. But then, depending on the array dimension, the array constructor has been applied 1 or 0 or multiple times. For example, it has just produced epsilon. Then it's a simple variable and we have no array constructor. So finally, so when I'm doing this reduction, so C, everything below C has been reduced already. So C has a type and C has a void, which is the type that T should get, which is the type that you have finally got. So you set C dot type to T dot type, C dot width to T dot width, and for the identifier ID, which was earlier entered in the symbol table from the lexical analysis time. You did not know the type at that time. So you look up and update the symbol table with the lexem of the ID and the type that you know now, which is the type T dot type, and the current value of offset. And then you update offset because you have the T dot type, you have the T dot width, which is the width of that type. So your offset is updated by that. There is no action to be taken for the other one. The remaining recursive part of this. So this also is an in situ action, as you can see. The actual rule is this. So you're writing the action right here after the semicolon. So in reality, what this means that you are actually introducing another non-terminal which produces an epsilon, and you are writing this action as a reduction action on that epsilon. So that it becomes one. Reproducing epsilon has no action. Now, for the rest of it, what do we have? These we know, 6 and 7. Reproducing it, so you know what is the type of weight. Reproducing float, again you know what is the type and weight. Reproducing B, it is the type that you have got in and the type that you weight that you have got in. And this is the point where you're setting the globals initially. So this gives you the basic type of element before your array construction starts. Because one of these is the first reduction. Let's go back. Under T, int reducing to B or float reducing to B is the first reduction. And then B reducing to T is the next reduction. And we still do not know the type of T because that depends on this C. How many array constructions we have. but we know the basic type that we have got through B. So we set that in terms of the global variables, T and W. Now, in terms of the array construction rule, this part, naturally the first thing, this is right recursive, the first rule that will reduce here is C producing epsilon. Even if it is not an array, C producing epsilon is going to happen. So at that point, you know what is the type you are talking about, which is a type set in this global. So you take T and set it to C dot. This is the C type of this. And similarly. So in rule 8, now you can recursively assume that you know the type of C1 and compute the type of C, which is very, very easy. Because if you know the type of C1, you know this dimension num. Therefore, all that you need to do is what is C? C is an array construction on this type of C1 type of element. So you just apply an array constructor. So that is how you can see that how type expressions are directly getting into your semantic action. So you put an array constructor for num dot value, which is the dimension, and the element type, and that expression is the new type of the left-hand side. What will be the width of that? Width of that is certainly the width of the element type, which is C1. So C1 dot width, and how many of those elements you have, which is num dot value. So C dot width becomes num dot value times C1 dot. So this is what becomes the C dot width. And if I go back again, so that is what you will get here as the final. So in this approach, you can actually translate the array declarations in a very easy manner, and using the type as you have done here and build up type. So actually, a couple of next slides I will not go through. These are okay. Let me stop once here.
There's a question on the previous slide.
Yes. What is the question?
Charuta asked whether the
T and W are global. Yes, yes. I said so. We are using that. You remember for inherited attributes, handling of inherited attributes, we are given 4 schemes. Of that, we are using the global scheme here. Yes. And then subsequently using it as you must have seen in the subsequent slide. So that's great. Any other question? No. Let me go back. Okay. Okay, so this is the basic scheme of translation. I have not taken a very elaborate example in this case because I thought you are by now pretty much of an expert. You can work out an example and get convinced that these rules will actually work for the cases. In the next couple of slides, which I'm not going to explain really here, are basically taken from the Dragon book. So you can see it uses a very similar kind of grammar. But it kind of uses either arrays through production tree, or it can also use a struct. So it can also define struct. And if you do struct, then the speciality is within the scope of the struct, you actually have a set of. So what is a struct? It's a series of declarations. Right? So you're basically making specifying the named components of the structure. So structure is nothing but a expansion of a D. So that is what we are specifying here. So you can see that this using this observation, you can very easily extend this whole scheme to not only process arrays, but you can actually very easily process structures as well. So this is just taken from the Dragon book. So I'm skipping that. These rules are also taken from the Dragon book, which are very similar to what you done. This rules are again from Dragon book. So that was just an example. I mean, those are. Dragon book specifies the grammar in a little different way, but it's a very equivalent. Now, before I close on this section, let me also highlight that, well, we have seen earlier that if one of the schemes of handling inherited attributes was to, you remember the schemes here. I mean, one was using globals that we are doing here. Other was to do a lazy evaluation, that is to keep everything pending and do it at the end. Lazy evaluation does not work in this case because it will be too much of information management, because you will have to collect all information about all different dimensions and then create all those type constructions and so on. Very clumsy. The third was using the Bison stack, using $-1, $-2. That too is not easy here because of the right recursion, because you do not know how deep the original value of the attribute in T is. So the fourth is, can you use rewrite the grammar to have synthesized, transform it to synthesized attribute. So here you observe that you have this problem because here in rule 4, you have the information reduced to T first, which you actually reduce. So, and so when you are reducing on C, you do not have this information from T, which is the case of the inherited attribute. So you would like to rewrite by using the in terms of the synthesized. But if you have done it in this way, because now you think that you have been able to handle this because you are reducing this together, then also you will find that that actually is not true. This design is actually, at this point in rule 4, it looks like that you have solved the problem of inherited attributes, because you are doing this T and C together, reduction in together, but that is not the case, because it will fail in rule 8 and 9. Because they will have to reduce before you reduce by rule 4. And when they reduce, you need this information. So just by changing into this does not actually make it into a grammar which is which can only deal with synthesized attributes. It is using synthesized attributes here. That's true. But here you still need the inherited attribute. Now this is where I started saying that I was harping upon the observation that you need right recursion. And this is where you'll see that the right recursion really makes it different. Because the moment you have right recursion, you do not know what is your depth in the parts tree or the Bison stack that you have got in, because your tree is right rotated. So you have you have taken all of that in the input, and then you start doing the reduction. In the left reduction, you get an input, you reduce, you get an input, you reduce. Here you take the whole thing in the stack and then you reduce. So information is lost somewhere deep down in your stack, and it is very difficult to synthesize it back. So this is an example to illustrate that, well, it sounds nice that, and we had argued that we will try to use the Bison stack, or we will try to use the rewrite of the grammar, having only synthesized attribute to make a clean scheme of translation. But this example will tell you that it is not so easy in every case. It is non-trivial to rewrite such a grammar, particularly a grammar that has a right recursion, because that goes against the basic principle of how to discover information from the stack. So this is this is just for your understanding that for such kind of a grammar, possibly we will think about what would be the refinements of the global scheme, or how that information can be managed in a proper way so that it does not get overwritten or destroyed in the process. Right, so this is okay. So that is all that I had in terms of the type expressions and declarations of arrays. So let me move on to the. Okay, should I stop once and check if there is any final question on the array?
There's one question.
Yeah, Shah, Ruta, we'll have to actually construct and see that. Why you can't use is the fact that you could, if you have a left recursion which you had earlier, then at every stage, your information that you want is right below the non-terminal that you are reducing. So your $-1 will have that. But when you have a right recursion, in the right recursion, all of your input, suppose the array has 3 dimensions. So the reduction will happen after all the 3 dimensions have gone into the stack. And only then you have C producing epsilon being reduced. So when you are reducing by C producing epsilon, you do not know whether it is $-1 or $-2 or $-7 or $-20. It depends on how many different dimensions have gone in. Because of this right recursion, because the tree is oriented in the right way. So the best way to and it's the same reason why you cannot do a synthesized attribute grammar easily for this. So I really do not know if one is at all possible. I don't think so. But this is, this is contradictory to the way we are doing the LR parsing. In the LR parsing, in the LR parsing, the whole scheme is from left to right, and you are going bottom up. So every time you reduce, you read an input and you reduce. You read an input and you reduce. Now, when you reduce, you have to have the information, inherited information on the stack on top, and at a depth that you know. Whereas when you have a right recursion, that recursion could give you an input stream which could be arbitrarily long, which you do not know how long it is. So you have to basically go back that whole, and that whole thing will have to come into the stack before you can actually start reducing. So at that point, you do not know how deep it is in the Bison stack. Now you can say, okay, I can keep on counting, I can do this, I can count how many symbols will go in and so on. But that becomes more clumsy than actually using the tool. So that's the basic reason. And but if you are not seeing it clearly, the best thing would be that take an example of say 2-dimensional array, an example of a 3-dimensional array. Try to just do the parse tree and draw the Bison stack, and you'll be able to see that how the depth of the inherited attribute information changes, making your stack Bison stack approach non-usable in this case. I do not know, Shah, if it answered your question.
Yes, sir. Yes.
Any other question? No. So let me basically.
Sir, is it possible to convert this into left recursion?
I mean, if you do that, I mean that's a basic problem I discussed. That you need the information from right to left. You can convert this to left recursion, but then your problem is you'll have to, your starting of computation is at the right end.
Yes, sir, understood.
So I mean, it's a basic nature of the problem that you have chosen. See, why are you doing LR parsing? You are the L of the LR is left to right scan of that. Why do you do that? Because your information naturally flows from left to right. It's not only that you write from left to right, but it's also that most of the information flows from left to right, because you are writing from left to right, and you writing from left to right, you always know what you have already written, and that based on that you write the next. So you have written x assigned 5 semicolon, then you are writing y assigned. So left to right is the best. So we have constructed a parsing technique which is LR, left to right scan. But this is one example, at least, where the information has to come from right to left, because you need to know the innermost dimension. And certainly it would have been extremely counterintuitive to write the innermost dimension first in the array expression. So then it would have been very difficult to use the arrays themselves. So it had to be written in this way. And that is the reason right recursion is the right way to form this grammar. And once you do that, you get into all these. So using global or refinements of the global scheme is the only option that we are left.
Thank you, sir.
Okay. So now let us get into. So this is the kind of last major section that we will do. That is, how do you handle functions? So in terms of functions, first we'll just deal the declaration. And to keep things simple initially, I deal with declarations, which I just prototyped, functions. So, and I have taken, I'm not taking a series of declarations, just a single declaration. So this is the type, this is a basic grammar for a signature of a function. Return type T followed by the function ID, and you have a pair of parentheses, and within that you have a set of formal parameters which may or may not be there. So I'm calling it f opt. So first, as in every case, I'm explaining the grammar. So f opt in rule 2 and 3 either gives epsilon, which means that there is no parameter, or it relates to f, which means there is one or more parameter. So f then goes into rule 4 and 5, where you have the exec in terms of rule 5, where it defines the only or the first parameter, and in rule 4 it has a left recursion. So this defines a series of list of parameters. So this is 2 to 5 gives you the sequence of parameters. Then you have the remaining is just to show you the types, which is we are using here an additional attribute which is pointed to symbol, so which we are calling as ST. So what we have done, if you look at the symbol table here, so what do I need to know from this declaration? The couple of things that I need. One is certainly the name of the function, which goes in the symbol table. Whatever scope it is in, the name goes into that symbol table. The type is function, right? And category is function. Whatever we were saying is category. The actual type builder type we will know later on. We just still do not know. And then we have the list of parameters and the return type. Now, I do not know how many parameters can be there. And I know that there has to be one return value. So, since I do not know how many parameters can be there, and for every parameter I need to know the type, and later on if you come to C++, the default possibility of having default value and so on. So certainly this is a case where the list of parameters of the function must be entered into a symbol table. So these parameters will also have to be created in a symbol table, which will actually become later on, when you have the function body, it will become a part of the function's symbol table. But right now you do not have the function body, you just have the signature. So it's a symbol table for that function which has to start getting created, with the parameters and the return value being specified with their tags. So in the symbol table global, if I say that this is a global function, I mean, similar thing will happen if the function, if it is a function in a different school, like in some class code or next. So if it is a symbol table if it is in the symbol table global, then it has a pointer to, this is nested table. So this pointer is the forward pointer to the types of parameters, or which will later on become the symbol table of that. So far, we have only maintained the information as a backward pointer. We have always kept the parent, but now we are keeping it a forward one, because given the function name, I have to check what the parameters are, what their types are. Is a call possible? So I have to know what is the symbol table where these parameters have been already specified. And this whole thing in terms of function declaration can happen before the function has been defined. So it can happen just with the signature. I can call a function just knowing the signature without actually knowing the definition. Right? So I need to know what is this pointer to the symbol table. So that becomes my additional attribute. Right? And then I have the attribute of type, width, etc. So rule 6 to 8 are trivial. The types are set. These are, whatever type it is. Now, what happens when you produce f? When f produces ei, you have got one parameter, and you know that is the first parameter. That is because of this left recursion. You know that this is the first parameter. Since you know this is the first parameter, it means that this has to go into the symbol table. Which symbol table? The symbol table of parameters, which later on will become the symbol table of the function. So what you need to do is to create a symbol table. So you create a new symbol table and keep that as f.st, which is an attribute. Because as you will come back to rule 4, you will need to keep on inserting all of the other parameters also in the same symbol. So you need to remember that. So f.st gets the create symbol. And once that has been done, now you need to enter this parameter into the symbol table. So you insert. In which symbol table are you inserting? That is the first parameter you pass to insert. That is f.st. So which is basically, if you look here, the st func example of int func double I, int I double d. So this is int I is the first thing that is being reduced, where st func has got created, and you are inserting in f.st, which is st func, the identifier I with t.type, which is int, and offset. I'm sorry, and the further pointer. This 0 is the pointer to this nested table. So further pointer is null, because this is just a variable, so it will not point to a symbol table. Now you'll see that subsequently that if this could be a more complex type, like a struct, this could also lead to another symbol table. But that's it. So I have created the symbol table and inserted the first parameter, and that becomes pointed to that symbol table, becomes the attribute of it. So if I come to rule 4, which is f produces f comma id, I'm getting the next parameter. Then I already have the symbol table f1, which is f1.st. I copy that to f because I have to work with that same symbol table. And this second parameter, which in this case is double d, will get inserted in that f.st, which is st func. I insert the idd, idd here, t.type, which is double, and it has no point. So I will keep on doing on this recursion, and as many parameters as I have, I'll keep on going, adding them one after the other. Then where will it reduce? It will reduce by rule 2. By rule 2, it will come to f opt. So all that I need to remember is what is the symbol. And I come to here. So here what have I got? I have got a pointer to the symbol table of parameters that I have already found. I have entered them and I have made that symbol table. So now I have to actually instead of insert it, this could be update also. Actually, on this function in the global, I have to put this function ID. So I put function that is in the ST global symbol table, the global one. This is a function identifier, which is func here. T dot type, which I'm simply written here as function, and the category is function. And what is the nested table? Nested table is what you have got in fopt.st, which is the pointer to the st function. So that is how the linkage gets done. The function is done. What is the remaining? The last thing remaining is this is the point where you have got a return type. So you have to insert that in the symbol table of parameters along with that, because then it will go into the symbol table of functions at a later point of time. So you insert in stfunc, which is fopt.st, the ret val. This is just a placeholder because return value does not have a name. So this is just a placeholder, right? Its type, the type is int, which you have got st.type, and certainly it has no further pointer. So you make this insertion, which creates the last row in this st function, and your function declaration has been processed. So this is the approach, very structured, simple approach that you can do. The only other case that is left is where you have opt producing epsilon, that is, there is no parameter at all. In that case, obviously you do not have in the other case in rule 2, you have the symbol table in F, which you could copy here. Obviously you do not have a symbol table. So you have to create a symbol table. Why do you have to create a symbol table even though there is no parameter? Because you need that symbol table to keep the type of the return value. Right? So fopt.st must be defined when I reduce by rule 1. So if I do not have any parameter, even then f produces epsilon as an action to create a symbol table and take that, set that pointer to fopt.st, which we use in rule 1 to insert the function and point to that symbol table, and then insert that symbol table, the type of it. So even if it does not take a parameter, this will get handled. So whatever I have discussed is illustrated here in terms of the actual parse tree that you get for this declaration and the computations that you do. We have already discussed this example. So before I go forward, let me check if there is any question. Tonmoy is asking, sir, if there is no parameters and the return type is also void. See, we can take this as OR as well. For example, return type could be void even when there are no parameters, and there are parameters, right? So we say, kind of earlier languages used to distinguish between function and procedure. Like Pascal had functions and procedures, functions which returned a value, procedures which did not return. C unified that, saying that there's nothing called, everything is a function, but a function can return nothing. So if the return type is void, then what will happen in the ret val? The type that you will have in the ret val will be marked as a type expression void. That's it. You do not have to. That's the beauty of introducing void as a zero of the type value. Otherwise, Every time you'll have to remember, is there a return type? Is there a type? Is there a parameter? You don't have to do all. Because if the return type is void, then you just enter it as void. Because that is the type expression. So if I just show you here, then I'm sorry. So if this were void, let's say if func were void, then when I enter return value here, I will simply enter void in place of it, and that represents. So what will mean that the size will be 0. Offset will not change, because if you have a void, then you are not expecting to actually allocate any memory location, because you are not expecting actually copy back any user or refer back. Does that answer you, Tanmay?
Yes.
Yes. Any other question? So let me go back. So we have just taken a look in the function declaration, that is signature. Now, two things. One is declaring the function, defining the function, and invoking. So that I have clubbed together into one, because the only way the signature just the signature declaration differs from a function definition is the fact that the first part, if you look at rule 0 here, TID within parenthesis f of this part, the signature part is found. So that's going to be there. And what you have is a function scope, which is in curly braces. You have a list of statements. That's all that you have. Right? That is the function scope. So it all boils down to, on one side, it all boils down to whether how you process a list of statements, which we have already seen. And this rule 1 and 2 we have seen plenty. So we already know how to process this one. So there's nothing to discuss here. The only specific thing that you might want to check out here is the two cases, choice between the two cases. One is where the function is already declared, that the signature has happened, and the case where the function is not declared. Now, if the function is already declared, then what will happen if I search the global symbol table with the function ID, I will get that entry. It's already defined. If this has already happened, before I provided its body again, then this will be there. So I will get that function on the global. But if it is not, signature is not given, then I will not get it. So depending on that, I can choose to either follow up on the actions or not. This will need a little bit of actions to be done, because as you can see that T will reduce first, and then all these FOX will reduce, and at that time you'll have to skip doing things, because you may have seen that already in the global symbol. What actually happens when the compiler is, even when a signature is already given, at the time of definition, the compiler will not skip processing. It will not construct a new symbol table, but it will still keep on checking that the parameters that you have given in the signature and the parameters that you specify here are of the same type in the same order. For example, if you had, say, given here as int func int I double d, and while you are trying to define a function, suppose func, you're saying int func int I int d, then the compiler will give you an error that the signature and this does not match in C. In C++, this has a bigger consequence, because in C++ it means that you are overloading them. So it does need to have a separate qualified name. We're not getting those, but those are the consequences. In C, this is relatively simple. So as you can see that handling the only thing that gets added in terms of the statements will be there will be a return statement. So in that, what all that you need to do is to check the type of this expression, which has to be E dot type, which will be computed in the way we have known. And then knowing E dot type, you'll have to check whether from the global symbol table, which you know from the scope here, because you are within this scope, so your parent is the global where your function exists. You'll have to check whether that matches with the return. So if it does not match, then you have this is again another type expression match. If it does not match, you have to decide what to do, implicit conversion, error, or whatever. If it does match, then you return the E dot log, which is the simple address statement for the return. So this handles the basic function definition case. So in the remaining part of the grammar, we actually talk about the function invocation. So function invocation is an expression. It produces the function name followed by a set of list of parameters, which are I'm calling as aopt, which is the actual parameters, and they are their grammar is written in the same way that F grammar was written. So aopt is epsilon or a, that is you may not have a parameter, or you may have. If you have, then you may have one actual parameter expression or multiple of them. So that's all that is happening here. The only difference in earlier, since you are doing formal parameters, you had their variable name or the parameter name. Here you have expressions, with respect to expressions. So what we assume here as an attribute is we assume that the a.opt has a list, which is a list of actual parameter expressions or the locations where these expression values can be copied from. So to start with, we have a.list, which is getting started with here. So in that list, we put the location, because that is from where you have to copy it to the formal variable, and the type, because you have to match that this invocation is correct, because every parameter has to match with the corresponding formal parameter. So you do a make list of the spare e dot type. Then you come up here in rule 7. So you have a1 dot list, and you have a new expression. So you will make a list for this e and merge it with whatever you have got. So in this way, your parameters are getting merged one after the, getting appended one after the. So you have a list of formal values in terms of e dot log, and for each we know the type. Now coming to the actual aopt, if aopt is epsilon, rule 6, then naturally you will not have a list to deal with, because there is no parameter, so the list is null. Otherwise, aopt dot list is a dot list, whatever. So what will come here, what you know is aopt dot list is a list of expression values with their types that are available. And ID is the function that you are trying to invoke. So you can look up the global symbol table with the ID. You'll get the pointer to this function entry, and the symbol table component will give you the symbol table of that function, which could be the symbol table of the function, or it could be the symbol table of just the function signature, depending on whether you have already defined the function or you are just defining it. So you will get that symbol table. So we are, when I look into this kind of an invocation here, then what I will get, if I may go back, what I'll get is a pointer to ST. This is what I'll get in ST. So I'll get that. And now I have the list of parameters, actual parameters. So for every param P in A of dot list, so I'll take each one, and each is a pair, a location and a type. So I'll match the type of P dot with the parameter type in ST. And this is by position. You'll see this is by position. So I'll just start from the top and keep on matching. You know, there are languages where parameters can be passed by name. Like I can say that parameter I is having a value 7, something like that. But here it is just by position. So in the symbol table, you have entered the formal parameters in an order. In aopt.list, you have entered the locations of the actual parameters in the order in which they're invoked. They have to match one to one. So you just keep on going over the list and the symbol table from top to bottom, match the type, and if they match, then you emit param p dot. So you are putting the param statement in the field. So all params done. If once the params are done, then what you need is to put the actual call to the function. So again, you will have to, for the call return value to be stored, you need the needed location, which is where this expression value will be kept, or e.log. So e.log does a gentemp. The only twist that we are giving here in the gentemp is, since we are checking the types, which is gentemp is not a blank call, but it is a call with the type of the function, which is type of the return value of the function. So which is, you do a lookup and get that type. You can get it like this, or you can actually go into the readval part of the function symbol table of stfunc and get that type. So summary, get the type of the return value and create a location of that type. So you know what is the type of, and then you emit e.log aside call ID, which is the format of the 3 address, and then you need to say how many parameters are there. When you have that, you have that in a.list. So you put that value as length of a.list. So that is what actually creates the function call. This is the handling of the function call with the function definition. So that will call a function irrespective of whatever you are doing. Now, of course, you will need some. I mean, if we are, I'm referring back to the response I was giving to Column 1. Is at this point, there may be an argument as to, can I really do an assignment here if the type is void? Obviously cannot. So those are specific cases which have to be handled based on that type here. So if the type is void, so you will not do a blind gentemp. First you will do extract the type of the return value. And if it is void, then you just do the call. Do not make an assignment. But if it is not void, then you make the call and assign. Of course, in general, the things may be a lot more complex, because if the type itself is a type expression, then you'll have to check whether you are allowed to copy it. And we'll not get into those. So below here is a simple example. We are continuing on the func. So you have ABC as int, DE as double, and you have this call. So obviously when you do B plus C will get evaluated using a part of the grammar which I am not showing here. So you'll have T1 as B plus C. Similarly, D into E will get evaluated as T2. And so these are, so once this gets evaluated, then your list will get started at A, which will have T1 and type as int, because B and C are int. then that will get into this list here in rule 8. Then I'll have D star, which will generate T2 assigned D star E, with T2 having a type which is double. So that T2 double will get appended in this by rule 7. So now I have two elements, T1 int and T2 double. So this is the list that I get. And that list now goes through the rule 5, come to here, and this is what I have. And I go over this one by one, and I have T1 as int, so I check the first one is int, matches. I have T2 as double. I go back and check, okay, T2 is double. So as I go over that, I do param T1, I do param T2. I look up this table to get that my return type is int. So I create a new location tree of type, and I call this function with a dot of list. This list has a length 2 with a value 2. Then finally, this assignment happens as a part of the grammar. So that's how a function call will get processed. Right here, I have shown it in more detailed work. And I can check through that, but this is necessary. I think this is straightforward after all that.
There seems to be an audio problem.
You're not being able to hear me, I see.
Now I can hear you.
So let me stop here once and see if there is any question.
There's one question.
Shunajana, sir, here it returns only one entry in symbol table and matches params with it. So overloading has not been handled. Yes, because it's a whole lot of different store. Overloading has not been handled. I'm just talking about C functions, C global functions. Overloading has not been handled. The member function issues have not been handled. Because the main issue of the overloading is we have in our scheme so far taken the names to be globally unique. But if you overload, then there's a func here takes int and double. I can overload and define a func which takes int and int, or int and say a structure. Now both of them are func by overloading rules, but to handle them distinctly based on the type, I need to give them different names, and that is called a fully qualified name. And there is a whole lot of schemes to how to do that and how to resolve which of these names actually is matching the overload. So it's a whole lot of additional issues which has to take care of this, and we will have to be. We cannot get to that depth of just a lack of time. But the whole idea is the whole approach. It has more dimensions, but the whole approach is very, very similar. It will again use symbol tables. It will again use matching and all that. But only point is it may not. It may have to match on multiple symbol tables very easily. Because if you have a function having two overloads, then how is the overload resolved at the fault time? It is resolved based on the types of parameters. So when you are matching the parameters, here we have assumed that you are matching the parameters by knowing what is the function. So here it is one way that I know the function. I've looked up the function in the global. I've gone to its symbol table. I'm matching parameter types one after. But if it is overloaded, I have at least two symbol tables corresponding to two overloaded versions of this function. And I have to keep on matching to see which version actually matches, or if at all any of the versions match. And based on that, I decide on the function. So there is a fundamental difference in terms of the approach in which you will have to handle overload. And that makes it a lot more complex. And then there are efficiency issues and so on. If you have 20 overloads of of the same function, and in every invocation you will have to process them parallel, then you are having a lot of operating time. So there are different schemes of compacting this whole list of. So all that you are trying to do now here is, if you take conceptually, Shona, then you are trying to take two lists of types, one that you have got from the invocation and one that exists in the symbol. So your problem, the algorithmic problem, reduces to taking two lists of type expressions and matching them. So there are smart algorithms. So these, I mean, we are not going to not being able to discuss them in depth, but these are the kind of issues and aspects that you have to get into once you get into this. Okay. Shahuruta Mitesh, what if the function is not declared yet? I mean, you certainly mean that it is being invoked, called before it is declared. So what will happen? Let's see. It should fail somewhere. So what happens? Let us go back to the invocation. So this is the invocation. You have processed AF.list up to AF.list. There is no problem. Then you are going to match. So you do a lookup here. So if it is not declared even as a signature till now, then this lookup is going to fail. So if this lookup fails, then you get a null pointer in ST or something like that. If this lookup fails, you know that the function is not declared. So it is, I mean, it's not that difficult to handle that. So you have the symbol table. So symbol table will always answer you all of this. Okay, Shah.
Sir, what declared in some other file and I'm calling from this file?
Yeah, that is the so you will get an error. So that is the reason you have the external declarations. Right? So the external declaration is another that we have not, wherein we say that this is declared somewhere else. Or you can just have that. You just need to have the signature. But I mean, in actual programming also, if you are invoking a function in file x.c, and you have the function defined in y.c, and in x.c you have not given the signature, then it's an error. That invocation is an error, because there is no way to find out. Because you will not be able to resolve that they are the same function till you go to the link type. Because your translation, all of the translation is limited to translation unit, which is typically a source file in C, C++ kind of language. So x.c will never know of y.c. Y.c will never know of x.c. So you will resolve this information only at link time. So in x.c, it has to be a complete. So it is required that you have that signature. The same thing happens for global variable. So you need to do external for the global variable. To say that I'm using this global variable here in x.c, but it is actually defined somewhere else. Now, the fact that the function called in x.c is defined in y.c, or a global variable referred in x.c is actually defined in y.c, are information that are resolved at the linking time. So if you recall Professor IST's discussions on that, this is the importance of linking. So when you have finally translated, you will keep a list of symbols that you could not resolve within this file. And every file will have that. And it will also have a list of information, a list of symbols which you know are defined in this. So the linker will correspond them and resolve them, and to see that every symbol is resolved, one. Second, there is no duplicate definition of the sense. Either of that is available. And those are the kind of errors we get typically. Okay. Does that answer?
Yes.
So just let me go back and close. We have almost time left. Today we lost a whole lot of time. So I couldn't do much. So Yes. Now, remaining of this module, I'm not walk you through in the remaining, but I'll just ask you to go through because that will help in your laboratory pretty much. Because quite a bit of the schemes has been detailed, which is the next one is how do you handle lexical scoring. So far we have just looked at a function scope separately. But if I have, so here I've tried to put the whole grammar together, starting from the program to variable declaration, function prototypes, everything. I'm putting everything together, all of these. And it's kind of close to tiny C grammar, but so in this, the thing that you will have to deal with is what if you have simple scopes in your within your function scope, and so within that you will have within that scope you will have to take care of. So this is this grammar deals with the global scope which we have dealt with, the function scope which we have also dealt with, but it also has nested block scopes. So just I have just tried to highlight the basic handling of the scope here, not detailing into all the other actions which have already been discussed for other rules. So just go through that. You should be able to follow it or make your own scheme. Because these are all part of the design. So it's not that if I'm presenting it in a certain way, X does not necessarily mean that you'll have to do the same thing to find a more smart way of doing the same thing. So you can see here in terms of this CS and this that I'm introducing the block scope, the nested scope at this point. So just go through that. Rest of it basically compilation of the whole thing, even with the simple set of features that we have done out of it. Over 40. Then given are some examples which in to a certain degree of detail I have worked them out with the parts tree and the actions that happen. So please go through them, try to work them out yourself. There's quite a bit of practice that you get from that in every type of case, particularly in terms of handling scope, which is very, very critical. So, you can see that the whole details very clear. So what I'm skipping in the direct discussions. And then I have a couple of slides on mentioning as to things that we did not actually do. It says handling of directives in C processor. I'll see. I mean, we exactly not sure as to when we are closing the semester. Depending on that, if I can get a couple of hours towards the end, I would like to do some more discussions, particularly in terms of handling of overloading and templates, because that's something very, very critical. But they are not part of the syllabus. So your syllabus ends, and even structure is not part of it. The syllabus ends at the scope. Managing up to the scope is what. Please go through this scope part. There are a whole lot of examples, and that should also help you in developing your own compiler as you are writing assignment. Let me go back and ask if there are any final questions. I had intended to do a little code today, but because of the loss of first half an hour, take that up. Any other question?
Nothing on the forum. Doesn't seem to be any more questions.
Okay, and there was the initial question on the syllabus of the test. So I will request the TAs to send out mails on that instead of taking it. Send out mails on that. So they are covering naturally the whole of parsing, both in theory as well as corresponding things that we have done in the Python. And the initial part of translation to intermediate code, that is up to control construct, right? I see.
Yes, yes.
Up to control. So arithmetic expression, Boolean expression, control construct. Declarations onward in the intermediate code will not be there in the syllabus, either in theory or in the lab assignment, lab quiz part. But I will request the respective TAs to print this, and Showman, if you can just send out the mails.
Okay, sir, I will do.
Okay. Okay, then thank you all very much. Sorry again about the mess up and the disturbances through the class today. I don't know what was that. But I have a good test on day after tomorrow. Looking forward to that, and details of login and all those will be. And one more thing I must mention, and Shuman also mentioned that when you send out the mail, is that the test duration this time would be of 1 hour. Each of the tests will be for 1 hour. Will be for 1 hour. We had last time kept 1 hour 15 minutes because of different uncertainties that we were apprehending, and things fortunately were more straight. And as we observed that most of you did not even use 1 hour of time to complete the test. So this time the test, each of the tests will be, quiz will be for 1 hour. So all the best for that for Thursday, and then we again meet in the class tutorial. Have a good day.